Hello everybody. In this video we're going to be covering section 10.3, phase transitions. Our first learning objective is going to be to define the phase transitions and phase transition temperatures. Then we're going to explain the relationship between phase transition temperatures and intermolecular forces. And finally we'll describe the processes represented by typical heating and cooling curves, compute the heat flows and enthalpy changes accompanying these processes. First, we're going to talk about condensation and vaporization. So vaporization is the phase transition from a liquid to a gas. Condensation is the phase transition from a gas to a liquid. This process is a dynamic equilibrium, and this is going to be a very important concept for us moving forward. It means that molecules are always moving between the two phases, even though the net amount of molecules that are in a liquid and the net amount of molecules that are a gas stay the same. I like to kind of think of it like a warehouse with boxes moving in and out. If you have the same number of boxes coming in as you have coming out, then you always have the same average number of boxes inside of the warehouse. This will be true even though the boxes that are in the warehouse aren't the same ones. The vapor pressure will determine where this equilibrium lies. It's going to depend on the identity of the substance and its temperature. When the partial pressure, so the pressure due to just that component, and the overall pressure above the liquid of a compound is equal to the vapor pressure, the equilibrium is reached. So it's important for us to understand the relationship between vapor pressure and temperature. And basically what's going to happen is in any kind of liquid we have a distribution of kinetic energies. At low temperatures we're going to have a very tight distribution. Most of our compounds are going to lie within a fairly tight range of kinetic energies. As the temperature increases, this is going to continue to flatten out and stretch further and further over to the right where we have higher and higher kinetic energies. This vertical line indicates the kinetic energy that's required for that liquid molecule to break free and escape into the gas phase. So basically you can think of it as the area underneath these curves is the amount of molecules that have the energy to reach out into the gas phase. Here we have a smaller amount, and as we increase the temperature we get a larger and larger area that is to the right of this barrier. So boiling. So this is important and it's really unique to this set of phase changes from the liquid phase to the gas phase and the gas phase to the liquid phase. Boiling is a different phenomenon than vaporization. We will have liquids that move out into the gas phase. For instance, a puddle of water sitting on the sidewalk will eventually evaporate away that are not boiling, right? What boiling is it occurs when the vapor pressure of the liquid exceeds the atmospheric pressure above the liquid. So all liquids have the atmospheric pressure pushing down on them. And if you get the temperature high enough that the vapor pressure of that substance exceeds it, that's when you start to see this rapid escape of molecules out into the atmosphere. The boiling point is a temperature at which this occurs, and it will depend on the atmospheric pressure. You may have heard something like it takes longer for water to boil at sea level than it does at higher altitudes and stuff. It's because at higher altitudes there's lower atmospheric pressure and it takes a little less energy to get all those molecules up to the point where the vapor pressure meets the atmospheric pressure. The normal boiling point is the boiling point of 1 atmosphere of pressure. Okay? During boiling, the temperature is going to remain constant. Right? The liquid isn't going to get any hotter, and the gas that escapes isn't going to be any hotter. It's going to be at the boiling point temperature. Okay, so how does this relate back to intermolecular forces? when the intermolecular forces between a liquid's molecules are stronger than the intermolecular forces between the liquid molecules and the air molecules, the vapor pressure will be relatively low. So that was a lot of words. Let's go back through that. Basically, what this is saying is that if the intermolecular forces between the liquid molecules and the air molecules are low, right? Meaning that the liquid molecules don't like to stick to air molecules, then what they're going to prefer to do is stay in the liquid phase and stick to one another. But when the intermolecular forces between the air and the liquid are stronger, the IMS between the liquid than the IMS between the liquid molecules, the vapor pressure will be relatively high. So, when the molecules are happy to stick to air molecules but not so keen to stick to one another, we're going to have a high vapor pressure. They're going to want to move out into the gas phase. Here we have an example of some various compounds here, right? And if we take a look at these and kind of analyze them, we have water, which has the ability to form 2 hydrogen bonds and pretty much has no other interactions going on. We have ethylene glycol that can form 2 hydrogen bonds but has these other components and dipoles interacting. We have ethanol that forms 1 hydrogen bond, and then we have diethyl ether that's only capable of forming dipole-dipole interactions. So if we're going to guess at the boiling point of these different compounds, we're going to say water is going to have the highest boiling point. Ethylene glycol is going to have the next highest boiling point. Ethanol will have a slightly lower boiling point than ethylene glycol, and the lowest boiling point is going to be diethyl ether. And that's the kind of trend that we would actually see in real life. We have the Clausius-Clapeyron equation. You're going to see this in our homework and in our quiz, okay? And it comes in 2 different forms, all right? We have this form here that's going to relate the pressure with the natural logarithm to the enthalpy of vaporization, which you would be given in the problem, the gas law constant, and the temperature. It has this additional factor here, A. This A is specific to which substance we are talking about. So if we know this A value for our substance, then we can use this equation and relate the temperature to the pressure, or relate it to the enthalpy of vaporization that we see. If we didn't know that, okay, what we can still do is relate 2 different states. All right, so we have this other form of the equation down here. And if we knew the pressure and temperature at one point, and we knew just one of whether either the pressure or the temperature at another point, then we could figure out the 4th point, basically. All right, so by knowing the full description of the substance at one temperature and pressure, we can figure out the temperature or pressure at another point. This is just one of our classic examples where we're just going to have to list out all of our different variables and decide which of these 2 equations we're going to use, and then start plugging and chugging our values out. It is important to remember that the R that we're going to use for this is going to be this one right here, where we have this joules, and that's going to relate and cancel out the joules that we're going to see in the enthalpy of vaporization. Just in case you forgot what the enthalpy of vaporization was, you should be remembering enthalpy from thermochemistry. And the enthalpy of vaporization is a special case of a phase change from liquid to gas. So if I have a very simple equation down here, like we have liquid water and then that goes to a gas, the enthalpy of that reaction is the enthalpy of vaporization. Because gases are always higher energy than liquids, the enthalpy of vaporization is always an endothermic reaction, and it's always going to be positive. However, the reverse of this is just going to be have a different sign here. Okay, so the enthalpy of condensation is going to be the negative of the enthalpy of vaporization. So let's talk a bit about melting and freezing. Melting is exactly what you think it is. It is the phase transition from a solid to a liquid. Freezing is the opposite of that. It's a transition from a liquid to a solid. The temperature at which this transition happens is the melting point or freezing point. So because it's happening at the same temperature, the melting point and the freezing point are the same thing. We only make a distinction depending on the direction that we're going. The enthalpy of fusion is the enthalpy of that process. And we actually have some data in Appendix G of our textbook. So you probably are going to come across some problems where you're not given the enthalpy of fusion even though you require it for the problem. And you need to go look that value up in that appendix. And again, the only difference between the enthalpy of fusion and the enthalpy of freezing is just the sign of the enthalpy. Sublimation is a little bit more exotic. This describes this transition from a solid to a gas. And the opposite of that is called deposition. This describes the transition from a gas to a solid. It seems like maybe we don't see this quite as often, but it actually happens quite a bit. Carbon dioxide can do this. We have dry ice, which is a solid, and then it will turn directly into a gas. Caffeine does this. They use that as a process to purify it in like industrial scale and stuff like that. And so this can happen quite a bit actually. And whether or not a compound will melt or sublime depends on its identity and the pressure and the temperature. And we're going to see that in the next section when we start talking about phase diagrams. The important takeaway here is that we have a certain amount of energy that is required to go from a solid to a liquid. This is usually the lowest amount of energy that we have to input, and that means that the enthalpy of fusion is usually the lowest of these three values. And then we have a little bit more energy that's required to go from a liquid to a gas. But in sublimation, we're going to require the most energy because we're actually going to go all the way from a solid to a gas in this scenario. The only difference here is that there is no stable liquid state at that temperature and pressure, so it has to go all the way to a gas. Okay, so heating curves. So it's important when we're doing these problems that we realize how to translate the language in the problem to a point on one of these curves so that we know exactly what it is that we need to do. The big takeaway here is that if I had, say I had a solid, right, and it was at a specific temperature, I'm right here. I need to, if I want to know how I got to another point, like say a gas up here, well, I first need to think about how much energy was required to go from that temperature up to its melting temperature, okay? And that is going to be our classic Q equals the mass times the specific heat times the change in temperature problem. And so I'm going to get that heat energy there. Then I need to figure out how much energy was required to actually melt it. Here I'm just going to be multiplying either the mass or the moles depending on what my enthalpy of vaporization units are. And I'm going to realize that the temperature isn't rising at this point, but I'm still inputting all of that energy. Then I need to figure out how much was required, how much energy was required to heat this liquid up to a gas, and then how much energy was required to vaporize that gas. Okay, so these are stepwise problems, and you need to realize what the steps are as you're going along. So every time you start a problem, you need to know, okay, what are the phase transitions that are going to occur between these two temperatures? what would be my enthalpy values that I need to know for those, whether the enthalpy of fusion or the enthalpy of vaporization or the enthalpy of sublimation. And then you need to know the various specific heat capacities, right? And the specific heat capacities aren't the same, right? The specific heat capacity of, say, solid ice is not the same as liquid water, and it's not the same as steam. So each one of these little lines going up where we're heating up actually has a different slope from the others. So you need to gather all that information together and then be thinking about, okay, what's happening at these various different temperatures. Conclusions. Each type of phase transition has its own enthalpy value associated with it. The sign of these enthalpy changes indicate direction. The magnitude indicates the strength of the IMFs, so the intermolecular forces. The Clausius-Clapeyron equation relates the pressure, temperature, and change in enthalpy of vaporization. And the temperature of a compound will remain constant during phase transitions.